All right, good evening, everybody. Had a little slide technical difficulty, so the session is profiling VR games and applications for mobile performance. My name is Kevin Hawkins. I lead several developer tools and outreach efforts at Qualcomm. I, in the past, have been in the VR space quite a bit, done a few things here and there. Today I'm going to kind of walk through why is mobile performance important, some of the developer tools that we have at Qualcomm to help you with mobile performance, and I'm going to go through a couple different use cases, how to use developer tools to profile your applications and understand the performance that you're getting in your VR app. And then we'll wrap up with questions, and I know the reception's afterwards, so you won't hurt my feelings if you have no questions. So quick introduction. Qualcomm Snapdragon processors, we are in a lot of Gear VR devices. It's a powerful system on chip. It has various processing capabilities that give better performance through heterogeneous computing, as we like to call it. Using all these different processors can give you better VR performance at lower power consumption if you know how to use them right. We do power the Galaxy S7, S7 Edge, and Note 7. These are just some of the features. The one thing to highlight here is our Adreno GPU getting 40% performance improvement over the previous generation, geared specifically for VR performance. That's really what we want you to know here. So mobile performance, why does it matter? It's pretty simple. Mobile users want performance. Study released last year, our survey, that was the #1 answer. In fact, 96% of mobile users just want things to work. They spend a lot of money on these devices, and as app developers, we are pretty much invited into their ecosystem. So we need to be responsible developers and make sure that we're not killing their battery, getting them sick in VR, or anything else that would kind of damage our reputation as developers. 80% give your app no more than 3 tries before uninstalling. 55% will blame you, the developer, for these problems. And 36% will stop using it if they find out that you're draining their battery. So these are all things that are relevant at VR, and Oculus themselves have said in their documentation that you want to be careful how you're using the system. If you're clocking the CPUs at too high of a frequency, then you're going to kill battery power. If you don't want to be pushing the code too hard on mobile. I'm going to skip this slide. It's not supposed to be in there. Kind of give you an example of this. This is a real use case using an application that's CPU bound. It was maximum clock frequencies on the CPU. And what was happening was the temperature was up. So at this particular point in time, and this is a screenshot from our profiler, this particular point in time, the profiler or the application had been running for about 12 to 13 minutes. And kind of think of the use case as a VR user. We have John, who's a VR, he's trying to play your app, and going through 12, 13 minutes in, feels the heat on his face, but thinks it's all just having fun. But then he gets to this point, and what happens is the thermal throttling, the scheduler, basically clocked the frequencies down, and suddenly everything starts to stutter. Well, John's going to rip that headset off, find a trash can, and maybe come back to your app later. But what's really kind of going on is it gets hot. The scheduler says, OK, collapse the frequencies. And in this particular case, it happened for an entire minute. The clock frequencies dropped to, I think it was 300 megahertz from 1.7 gigahertz, and didn't let it go back to normal operation until the system had cooled down. So it's something to be aware of. Kind of go back to that real quick. Something to be aware of, because with VR, this particular app was pushing the CPU really hard. You don't want to be doing that with your VR apps if you can help it. And we do have some things that can help you with that. So talking about developer tools at Qualcomm, these are some of the tools that we have. The ones that I'll specifically be highlighting are the Symphony SDK, our Snapdragon profiler. I'll be going into a lot more detail about that, and the Adreno SDK. And these are all available at developer.qualcomm.com. The Symphony SDK is Yeah, this is tough because the slide's different now, but basically it simplifies concurrency for you. So if you want to do parallel or do a lot of concurrent tasks across the CPU and the GPU, Symphony's built to help you do that easier. It will take care of the scheduling, the power management, finding the most optimum way to execute your code. It also has a power API that you can use to set different power modes, which will impact the clock frequencies. And there's also, it's a user space library. You can also download it for free from our developer portal. The reason I wanted to mention it, though, is we actually have a really great use case about this concept of not pushing the clock frequencies. Here, this use case was a hand detection app. The detection time was taking about 50 milliseconds to execute. And the point I want you to be aware of is that the algorithm was executing on one core at 2.1 gigahertz. And it would take roughly 5 seconds to execute the full thing, and the total energy consumption was about 5.1 joules. When we used Symphony, Symphony decided, well, we don't want to max the clock frequency on that CPU, even though it's just one core. We want to use 4 cores and use them at 1 gigahertz. The net result was a 29% power decrease and bonus 10 degrees Celsius decrease in temperature. Symphony is great to help with that. And you also get the 28 milliseconds of detection time. So they got the perf improvement, less energy being used, and less temperature. Symphony is great for helping with that. The main point, though, is what I've been saying before, and what Oculus has in their guide. Don't push the clock frequencies. Be smart about what you're executing and how you're executing it. The next tool is Snapdragon Profiler, and this is our system profiler. You profile across the CPU, the GPU, the DSP, looking at power, thermal, looking at network data. Basically everything that's happening on the SoC, we try to provide information for you. We have been working with various partners to make it better for virtual reality applications and understanding what's happening there. And it's plug and play, so you can use it over USB or Wi-Fi. Works across major desktop platforms. It focuses on Android targets. We do support all the major Chronos APIs, including Vulkan. And the one caveat is that it works with Snapdragon 805 and newer devices. So I want to provide a really quick overview of the major modes in Profiler, just so you know what you're looking at later. The first is what we call our real-time view, and this is, as it sounds, looking at real-time data. Pretty low sampling rate, really good for just understanding generally what's happening in the system at a very high level. The next one is our trace, and in this screenshot, we have DSP in the top area, we have GPU data in the middle, and Android systrace kind of at the bottom. So what we actually did was took Android systrace, trace kernel data, and started instrumenting with our driver and for the graphics driver, and getting data out of our DSP as well, so you could see a complete system view on the same timeline of what's going on. The snapshot mode is our frame captures, if you're familiar with GPU debugging tools. We'll kind of dig into that a little bit. So let's get to the fun part, the guidelines. Wanted to make a comment about asynchronous time warp. I believe Oculus kind of covers this too, but just to kind of reiterate, asynchronous time warp is definitely your best friend, but it's also your worst enemy if you're not aware of what's really going on. Profilers, our profiler in particular, can help you understand that, so that you know how often is asynchronous time warp executing, when is it executing, how is it working with my frame, and we'll kind of cover that. So what we did for these use cases, we took the CubeWorld application in the Oculus SDK, made different modifications for different test cases, analyzed the performance with Snapdragon Profiler, and we used the Galaxy S7, which has a Snapdragon 820 in it. So the first thing we did is, when making our modifications, is said, okay, well, what's the structure of the frame? So we did a snapshot. And with the snapshot, you get the screenshot there in the top section, and on the right-hand side, you get all your resources, including your textures. And in the bottom middle, you can see all the draw calls, and you can dig into the API calls and see what's going on. On the left side, program attributes, and down below that is the shader code for different programs. So when we took that shot, the first thing we did is say, okay, well, where's the two eye renders happening? And we found these two draw calls, the left eye being draw 5 and the right eye being draw 11. And then we said, okay, from there, we have our time warp context. The rightmost column of that view is the context for the draw calls. So the time warp context there at the top, and then the middle section being our app context, and then we have time warp again. So the first use case we looked at was GMM Loads, and the Oculus guide talks about, or has a line about, avoid bin fills from main memory and unnecessary buffer writes. It's basically what we call GMM Loads, or avoid GMM Loads. And if you're not aware of GMM, I'm talking about graphics memory. So GMM Loads are the operation of loading a render buffer into graphics memory. It's affects tiling architectures, which Adreno is. And this mainly is because of the binning that we have in tiling architectures. In this case, the driver assumes that the contents of the render buffer need to be preserved. And I'm not going to go into a lot of detail about GMM Loads. If you're interested in that, we do have an Adreno developer guide that you can check out. The problem with GMM Loads is that they're using unnecessary GPU cycles. We need to tell the driver that it doesn't need to load the render buffer into GMM. And how do we do this? Oculus recommends doing invalidates, but invalidate or clear the frame buffers and clear all the attachments. So when we look at it in Profiler, the first thing we did was just no GMM Loads the way the app actually is. We didn't actually modify the code here, except for adding a skybox using one of the cubes from Cube World. So what we're looking at is a trace view, and we can see kind of the bottom section there is the information coming out of the graphics driver. So we can see the surfaces that are being processed. The red surface there is selected. So on the right side, you can see the attributes for that surface. We can see that there's 40 bins being created for that surface. We'll get to the rest later. Taking 4.5 milliseconds to execute. And then below that, we have each of the binning, the different stages that are executing in the driver. So binning, render, and GMM stores in this case. And we can see how much time each of those are taking. So we know from looking at the structure of the frame that each of these major blocks is the eye rendering. It's the left eye surface, the right eye surface. And we also know that time warp is preempting them and technically adding more time to our frame. Here's a more detailed view, zooming in on one of the surfaces. So you can see in the render line, each of these blocks is basically 40 blocks for the 40 bins. That's each of the bins being rendered. And you can see on the second surface that asynchronous time warp is preempting on the GPU. In this case, the total frame time is about 11.6 milliseconds. The preemption time about 2.4. So all in all, no big deal. That's kind of what we would expect with no GMM Loads. So what we did was we created GMM Loads. We wanted to see what's the impact of adding this in. So we purposely, in the clear call, took out the color buffer clear and just left the depth buffer. And because we added the skybox, the app renders fine. It's not even something that's noticeable that we technically do have GMM Loads now. But when we do another trace capture, we have a new line for GMM Loads. And there you can see basically per surface for the 40 bins, you're getting GMM Loads. And the impact of this is pretty large. Now the surfaces are taking, in total time, 8.73 milliseconds. Asynchronous time warp roughly 2.5. So when you look at how much is your render time taking, it's roughly 6.2 milliseconds, and that's up from 4.5. So basically per eye, you're looking at 1.7 milliseconds extra. When you're talking about 16 milliseconds of time, that's a lot. So, like I said, the driver thinks the color content of the bound buffer is needed, so it's going to bring it back into GMM. So what we need to do, the proper fix, is to keep that color clear in the code. So the second use case would be mipmaps. And from the guide, the GL generate mipmaps is fast and efficient. You should build mipmaps even for dynamic textures and, of course, for static textures. And yours truly forgot a parentheses, so sorry about that. Just to review, generate mipmaps, basically building lower resolution versions of the texture. And the problem is we're rendering to a 1K by 1K eye buffer, so there's no need to be using a 1K by 1K texture in all cases. So again, what we did, took the cube world, added a 1K by 1K uncompressed texture to all the cubes, and we created two versions of this app. One that used the raw texture and one that used the generated mipmaps. Took a snapshot. There you can see the screenshot. Really artistic kind of screenshot now that we added the Snapdragon texture. And we zoom into our textures area, and we can see, yep, we have a 1024 by 1024 texture, and we only have one MIP level. So this is the raw, no mipmaps application. When we look at the trace to see the performance of this, we select our surface, and the surface is being preempted twice because it's taking so long. So total preemption time of 4.7 milliseconds being added to our frame. Basically comes out to almost 11 milliseconds per eye. Total surface time being about 15.5 milliseconds. So it's pretty significant. That's not going to work for VR in any way. So what we then said, well, why exactly is this happening? We went into our real-time mode and added our metric for texture fetch stalls. Basically, how much time is the GPU spending stalling, fetching texture data? And in this case, when we're not using mipmaps, it's basically half of its time it's stalling. So definitely not good. So we added our mipmaps in the next case. Took our snapshot. Confirmed again, 1K by 1K texture, but the MIP levels are now 11. So the point here is Snapdragon Profiler can help you confirm that you're getting your mipmaps and other information that you would expect to get from your code. When we looked at trace, pretty significant, almost half the time now to render each surface. Duration for the eye rendering now is 8.27 milliseconds in total. When we take away the time warp preemption, we're looking at 5.5-ish milliseconds per eye, so 11 milliseconds for your total render time, not including time warp. So then we went back to the real-time view, and now we're looking at about 4% of stalls, or time GPU is stalled. So pretty significant drop. And then we, for fun, decided to run the one without and then the one with in real-time view, just so you can see the relative measure. Pretty significant difference. I think it kind of shows the importance of these types of optimizations. You also notice that the GPU utilization went down pretty significantly. We didn't actually find out what that value was, but you can obviously see it in the visualization. The third use case is texture compression. And in the Oculus guide, texture compression offers significant performance benefits. So we took the CubeWorld app, took our 1K by 1K texture, compressed it with ETC2, and again created two versions for the test. Now the one note here is we don't have the mipmaps now. This was a totally new isolated test. When we got our trace, again, using the same test that we had before, this is no mipmap, just using the raw texture. As a reminder, we were taking almost 11 milliseconds per eye. And the GPU is spending about half the time on stalls. So really the change was get our compressed texture and then actually use it, making the call to compress text image 2D. And when we ran the trace now, the surface time 8.7 milliseconds. Maybe not as huge of a drop as you might expect, but still significant. Still shows the importance of compressed textures. So take away the time warp preemption, and you're looking at 6.2 milliseconds per eye, or roughly a 4.6 millisecond decrease. Again, that's pretty decent for VR. I wouldn't say that's necessarily ideal. You're still getting a 35% fetch stall with the compressed textures and not having the bitmaps. So again, kind of doing the relative performance. Definitely not an ideal scenario, but it is better. Just kind of a side note, the little spike there in the middle is pressing the app to launch it. So the last thing I wanted to mention is sometimes people bring up texture compression as hurting quality. The Adreno texture tool that we have in the Adreno SDK can help you see the difference in quality between uncompressed versus compressed. And you can see, I'm not sure how well it's showing up there, but it's pretty minimal in this particular case. It is a very simple texture, but tools like this do exist to help you there. And to wrap up, kind of recap, I talked about mobile performance. It's important for users. Users want performance, and as developers, we need to be aware of that. We need to be responsible for that. You can use tools like Snapdragon Profiler to help you understand how your VR app is performing. Asynchronous time warp is great, but it's not a silver bullet. You still need to make sure that you're meeting the 16 millisecond time to get the best VR experience. Like I said, Profiler can help you with that, help you understand exactly what's happening in the driver. And then showed a few use cases. I kind of recommend going through the Oculus guidelines and seeing for yourself, using a tool like Profiler to see what's going on. And you can learn more and download Profiler and all the other tools at developer.qualcomm.com.